talk of this morning is by José Luís da Silva from the University of Madeira. So he's going to talk about green measures for non-local diffusion equations.
Okay, thank you very much for the presentation, and thank you for the organizers of the very interesting workshop. Unfortunately, I cannot be present. My initial plan was to be present on the workshop, but unfortunately, due to many kind of variables, I could not join. Also, I have a quite busy semester. I have 10 hours lecture this semester, and shifting all these lectures will be a nightmare. So I decided to participate online. Okay, so about this work, this is a joint work with Yuri Kondratiev, which was supporting this event for a long time ago, which this was shifted for already, I think, 2 years. And this is somehow a recent work which is still ongoing. We did not finish this yet. But some of the ideas are based on some early works, which I also present today. Okay, so about the outline of the talks, I will present some kind of general framework about the contents of the talk, and then especially the definition of the green measure associated to this Markov process, and then I will concentrate on especially on the jump generators and green measures. If time allows, I will go a little bit on the time change of Markov process at the end. Okay, so the setup of the problem is the following. So you consider a Markov process in RD starting from X, and then you define such object, which is V of X. So V of X, V of f of f on X, which is equal to the integral of the expectation f applied to xt, and then you integrate with respect to z. So this object is known as the potential of the function f. And of course, if the existence of this this quantity is not easy, and depending on the process, also depending on the class of functions f which you are interested in, so to settle this existence can be more or less complicated. Okay, so in our case, we will just represent this object in the following form. So we just represent this as an integral in RD, f of y, and then you have a measure, okay? Measure in RD, which depends on x, which is the initial point, okay? So you see here, you can see this measure in different ways, yeah? So you can see this, for example, as the image measure of the product measure, or you can see this as a kind of occupation measure, for example, and so on. Or in addition, you can also see this as a kind of a fundamental solution for this equation, which is here, yeah? So L is the generator of the process X, okay? So then we call this the green measure for the operator L. And so the idea is how to define this measure in a proper way, depending on the process, also on the class of functions. Okay, so the problem somehow is I will concentrate on the case of non-local diffusions, where the generator is of convolution type, and somehow the main difficulty is related to the dimension, and especially if dimension is 1 and 2, then it's more complicated to show the existence. Okay, so we have some results now for bigger than then bigger or equal than 2, but also for, in some special case, for d equal 1. Okay, so that's somehow the problem. And now let's go to somehow to settle down a bit more the details. So here I just give a little overview what about Markov semigroup. So I have a Markov semigroup which I denoted by TT. Okay, and this family is defined in a Banach space, which you can take in different, different types of, different spaces, either bounded functions, continuous bounded, or some LP. Yeah, so it depends on each case you are interested in. Okay, and then this semi-group, we associated the Markov process in the following way. So the TT applied to F on the point X is equal to the expectation applied to F of X of T. And then you can write this as F of X, F of Y, and then you have the probability of the transition. Okay. So this probability of the transition you can recover from the semi-group, okay, and if you put just the TT applied to characteristic function, okay, and now it's clear from here that if you go back to the definition of the green measure, now it's clear that the green measure somehow you can write it in that way here, yeah, just integral from 0 to infinity of this transition probability dy, and then you integrate with respect to t. Okay, so that's somehow the framework, and now we just give the definition. So a green measure for the Markov process X with transition probability PTXB is defined in this way. So you just apply the green measure on the Borel set B. It's by definition the integral of the transition probability on the set B, and then you integrate with respect to t. Okay, or if you want, if you can make just you can just make this for any compact continuous function. You can just make the integral of the green measure equal to the integral with respect to the transition probability. Of course, if these integrals exist, yeah, because it's not clear that these integrals exist always. Okay, so that's the definition of the green measure, and then you can just use this the relation between the semi-group and the generator in order to write the green measure as the sum of the minus the inverse of the generator applied to F on the point X. Okay, so then you integrate. You have the integral of F with respect to the green measure equal to this inverse operator. Okay, so such that we can see the green measure as the fundamental solution for this for the corresponding generator of the process. Okay, in case the measure as a kind of density, then we could write this as a density G in Y, but typically this density will be a generalized function, positive generalized function. Okay, for each X in RD. Okay, so now let's define the type of kernels, jump kernels, which we are interested for this process, the Markov process. So we will concentrate in kernels. We call them A. Yeah, we call them A. These are kernels which satisfies the following condition. They are symmetric, positive, bounded, and continuous, and they are integrable. So that means they are densities. Yeah, and in addition, we put here one condition somehow which is a bit different from the previous works we did it. So we assume the following condition on the Fourier transform. So you can write it as 1 minus constant modulus of k power alpha. Alpha is and plus some small o of modulus of k power alpha. And alpha is between 0 and 2. Can be 2, but also can be smaller than 2. Okay, so typically this condition is, substituted by the second moment of A, which here we don't assume. Okay, so there are cases where this does not exist and this condition is still true. Okay, so I will give you some examples. For example, the first example here about the Gaussian kernel, of course, in that case, the second moment exists. Yeah, it's clear. Okay, so then you can write the Fourier transform of A in this way. So it's 1 minus k squared modulus of k squared plus some other terms. Okay, so but as I said, the second moment for this case exists, but in general, we can cover with this Fourier transform, which I put it before on A, we can cover cases where it fails. Okay, such that we have more general expansions of the Fourier transform. And the typical example is this Cauchy distribution. And now we have here, so we have for the Fourier transform, we have 1 minus modulus of k plus other terms. Okay, so in this case, the second moment does not exist. Okay, so then the jump generator corresponding to this jump kernel, it's a convolution operator. So we see the L applied to f on x is just a convolution of the kernel A with f, and then you subtract f of x. Okay, so this operator has nice properties, and it was studied by many people already, and also equations using this operator were studied in the literature by many people also, especially the group of Rossi and co-authors, studying the long time behavior of the solution associated to the equation of this operator, evolution equation associated to this operator.
Ja myślę, że przez Google Chrome to
Pardon? Anyway, somebody was, I did not understand. So, and then we call this operator the jump generator with jump kernel A, okay? The corresponding Markov process is also well known, and it corresponds to the compound Poisson process. Of course, you see in terms of the Fourier variables, this operator L corresponds to the multiplication by this quantity here, which is simple to see. Yeah. So as I said, there were some or quite a lot of interest on this operator in the recent years. Here I just mentioned some of these works by the group of Yuri and some other co-authors around the studies of this kind of operator. Okay. So in order to find the green measure associated to this operator, so we go via the resolvent of the operator lambda minus L1 power minus 1, and the kernel of this resolvent admits this kind of decomposition here. Okay, so you see it is a sum of a distribution which is somehow a singular part, and then you have another function which is a bit more regular, which is given in terms of the kernel A, okay, which is some kind of, it's a series of the kernel A, but you have the convolution n times, yeah, on the series. I mean, you can see this kind of the decomposition somehow using the Fourier transform also, yeah. And of course, we are interested on the case where, where lambda is equal to 0, yeah, which corresponds to the L minus 1. And if the kernel A, the jump kernel, satisfy the above assumptions, yeah, then the green measure for this random walk exists if I have this condition here, which is D is bigger than alpha. Okay, so alpha is between 0 and 2. Okay, so the proof somehow is relies on the Fourier transform and the representation of G0 using the Fourier transform, which can be seen from the previous expression, yeah, from this expression here. Okay, and then you just of course you can just compute this using you can compute this using some kind of Neumann type series and so on. Okay, and of course now this integral here exists. Yeah, this integral exists because of our conditions on the kernel A. Okay, the condition on the Fourier transform somehow guarantees the existence of the integral, especially on the around 0, yeah, because of the singularity. Okay, so here there are some examples of kernels. Here, for example, the first one is the Gaussian kernel. Okay, so in this case we can estimate, for example, we can estimate even G. Yeah, so we can estimate G0x, which is smaller than constant times exponential, and then you have models of x squared, and there is some constant. Okay, so this is computable because we can compute or at least estimate. Yeah. Okay, the estimation is done. Yeah, first you have to compute the kind of convolution of this operator n times, which is somehow easy to do, and then you have to plug in on the series, and then you can make this estimation. Okay, so the other term, which also it's some kind of exponential tail. So you have A is a constant times some exponential decay of order 1. Okay, so on that case, the G0 is bounded also by this exponential. Okay, so this result, somehow this result is taken from the paper of Yuri and some co-authors on 2018. So the convolution operator A of this exponential tail, yeah, type, you can estimate using you can estimate this convolution using this inequality here. Oh, this convolution allows this estimation, and then plugging in this on the series, then you can get the estimation for G0 also, yeah, because then you have the series somehow of series of 1 over n power d over 2, and if d is bigger than 2, then the thing is convergent. Okay, so another case is the Brownian motion. So in this case, the generator is the Laplacian. Okay, and for that case, of course, we can also compute explicitly the green measure. Okay, so and here I introduce the space of functions f such that we can handle the green measure. So the space is called the CLRD. So these are continuous functions which are bounded and L1. Okay, and on this space I introduced the following norm. Okay, so this norm is the sum of L1 and the infinity norm. Okay. So, and on that case here we have D bigger than 3, bigger or equal than 3. And this case, the green measure is given by, so here we have a density, yeah, and then we have dx. And you see the proof somehow is just the convergence of the integral, yeah, the convergence of this integral here, which somehow we divide in two parts. One is the smaller than 1, the other one is bigger than 1. And in one of them, we can bound using the infinite norm of f, and then the convergence of the integral. And the other one, you can bound by a constant times the L1 norm of f. And then as a result, this integral is finite, and so the green measure so exists. Okay, so we still have 5 minutes. So let me just speak a little bit about random time process. So if you have a Markov process and then you change the time using a kind of random time, okay, like was spoken before with different time things. I mean, there is many ways how to change the time of the process. You see here we have the process. Somehow you have a Markov process, and then you define the function u using this expectation. Okay, and of course u is the solution of this Kolmogorov equation. Yeah, so the time derivative is equal to the generated applied to the u of t, tx. Okay, with some initial condition. Okay, some initial condition f of x. Okay, and now I want to, instead of x, I want to change x with a certain time change. Yeah, so I call this et, and this is the inverse of a subordinator, which in that case, as was mentioned on the lecture before, on that case, I take independent of the base process x, okay? So then we can just construct again the same type of expectation as we did for x, and then now this function v of t, instead of this Kolmogorov equation, now it satisfies this fractional evolution equation related to the fractional derivative of this kind of density Vt, but with the same L, yeah, with the same L. K is a kernel, and the definition of this derivative, or here it should be, I mean, here should be the same, the same d as it is defined below. Okay. So the definition is given here on that form on the equation number 8. It's the convolution, the convolution of the kernel with u, and then minus k of t u of 0. Okay, and then you make the derivative. There is a derivative before the convolution, of course. Okay, why this does not go on? And you see, we have by the subordination formula, we can represent this the solution, yeah, Vtx using the original solution in terms of u, and here you have the density of the inverse of this inverse subordinator. Okay, sorry. And yeah, and now you see how to construct the green measure for this process, Markov process, time change Markov process. You see, of course, in terms of the density, the marginal distributions, we have such kind of equality here. Yeah, the marginal density of the time change process is equal to the integral, and then you integrate the marginal of the base Markov process X against the density of the time change. Okay, and of course, you see this implies that heuristically this green measure for the time change process Y, it will be something like, the integral with respect to PT, which is the transition probability of the base process, and then you integrate with respect to the density of the time change. Okay. The problem is that if you do in this way, yeah, typically this existence of this green measure will be. I cannot move this anymore. I mean, the existence, so here I define, of course, yeah, I give the definition of the green measure as the integral of the density of the process Y, and then I integrate with respect to T, but it's you see, it's a very simple consequence of this construction that in general this this measure as it is defined, it does not exist. Okay, I mean, this is somehow a consequence of a result which we have on 2020, which somehow goes down and to the integration of the density of the inverse subordinator, which is plus infinity. Okay, and what happens here is instead of that definition, we have to renormalize. We have to renormalize this measure. So you see, instead of taking that quantity as the green measure, we normalize it and then we make a limit. Okay, and the good thing somehow is that you see, taking a very proper normalization, which I put it here, okay, n of t is equal to the integral 0t of the kernel k. You see this kernel k is is somehow this function L1, which you define the fractional derivative, and then what happens is that you see the renormalized green measure somehow is equivalent or is the same as the green measure when the limit, when this limit t goes to infinity. Okay, so this green measure is a kind of universal property. Okay, the proof of this, of course, I did not put here the details of this construction, but the proof of this somehow relies on a theorem from our previous paper, which is somehow this kind of quotient, which is equal to 1. Okay, so and that's why we get this normalization somehow equal to the green measure. So that's somehow the result for this time change. Here I have some of these references which I put it here from the people which already studied this convolution type operators, and that's all. Okay, thank you.
So thank you very much. So are there some questions, some remarks? Maybe I have one, but I'm sorry, maybe. You obtained a renormalized green measure for your process Y. But initially, the green measure for the Markov process is essentially related to a solution of an equation where the generator of the process appears, right?
Yeah, I mean, so,
and can you say something about this renormalized green measure also? Is it related to the sort of generator of the process Y, or?
Of course, you see here, so you see here inside, of course, I mean, that measure here somehow, you see, this is the distribution of the time change, yeah?
Yes.
And of course, that one as take into account the original one, yeah?
Yeah.
It should take into account because, you know, it's related to that one. I mean, if you write down this marginal, of course, you will get also the marginal of the original process. And then, of course, this is related to the original green measure. Yeah.
Okay. Yes, another question.
Hi, José Luís and Michael speaking. I have a question concerning the green function without renormalization. I mean, when you do this inverse subordination, then of course it can happen. The process sits in a point for a long, long time. Yeah.
Yeah.
And then this integral will never be finite because it's the expected time to be in this dy. I mean, in this little, let's say, infinitesimal set. But can you characterize the type of, or at least give a sufficient condition for the type of inverse subordination you can take in order to have a green measure? So that means that this measure, well, if it's a measure, it could be plus infinity, probably you mean Radon measure. So that means finite on compacts or something.
Yeah.
But do you have a sufficient condition on the subordinator so that this is a Radon, really a Radon kernel?
Yeah, I mean, we explore only this, the inverse of a subordinator.
Yes,
yeah?
That's what I mean. I mean, you just, can you characterize which kind of subordinators you can take when you inverse subordinate to have a finite green kernel or a Radon green kernel?
So, yeah, I mean, of course, there is a, you know, somehow it's related to this result which we have here. And we have a kind of admissible kernels, yeah? So you see, this is related to these kernels, and we have a kind of class of admissible kernels such that this result is true, yeah. Okay. And that somehow is based on this result here. Mm-hmm. Yeah, and
can you give what is n of t? Can you give an idea? Because you say you renormalize by n of t, but what is capital N of t on the previous slide?
N of t is this one here.
Okay. See that? No, I understand.
Yeah, so it's this quantity here.
Right.
Yeah.
Right.
Yeah. Okay. And you see, and so that's somehow the choice of n of t such that this work. But of course, the class of subordinators is encoded on that equation here. Yeah. So somehow there is a kind of, you know, class of subordinators such that this condition holds. That's right. Yeah.
Thank you. Okay. Very nice. Very nice. Mm-hmm. Thank you.
One more question. A question online. Yes.
Thank you for the nice talk. Thank you very much. I just have a very simple question. Is it possible to calculate examples?
To calculate
examples. So do you have examples? Have you, especially with the
examples of this time change?
Mm-hmm.
I mean, somehow I did this somehow in an abstract way, but I mean, we could concentrate on this, you know, I mean, the classical example for, yeah, I mean, there are examples. I mean, you know, the stable case, for example, the stable case, what else? We have some other examples. I mean, maybe what the example, the gamma case, I guess, we have also as an example, which satisfies such condition, for example. So I mean, on that paper, I think on that paper we have some such a list of examples there. Yeah. Yes, I mean, in one of these papers, I have quite, I mean, 3 or 4 examples, which are somehow also known in the literature.
Okay,
Yeah.
Thank you very much. Thank you.
Welcome.
Thank you. Thank you. Is there one last question for the morning? No? Okay, so we thank José again, José Luís again.
Thank you very much.
All the speakers of this morning, and so we resume first.